thought I would discuss this question because it's a different take on the required practical on thermal insulation that they have said they will assess this year for separates. So we've got, student investigated the properties of 3 types of insulation. So remember, insulation has a low thermal conductivity, which means it transfers energy across it at a low rate. So figure 1 shows the apparatus the student used. So we've got a hot metal plate kept at a constant temperature and an insulating material. And we've got a temperature probe 1 that is inside the hot metal that's being maintained at constant temperature. In fact, it's telling us here, temperature probes measure the temperature on each side of the insulating material. Okay, so the insulating material where it's connected to the hot plate, and the temperature probe 2 on the other side. So that's looking at how much heat has transferred through this insulating material. So in the required practical that you've learnt, you start with something hot that is cooling down. Here you've got an insulating material that is being heated up. Okay, so we are expecting that if something is a good conductor, has a high thermal conductivity, a poor insulator, that heat will transfer across quickly and the temperature of probe 2 will rise quickly. If something is a good insulator, it has a low thermal conductivity and transfers energy at a low rate, then the heat from the metal plate won't transfer across the insulating material very quickly at all, and the temperature of probe 2 will rise slowly. So that's kind of the opposite of the practical you did where you're looking at the hot water cooling down. You're still expecting hot water cooling down wrapped in insulator. Okay, if it was a good insulator, you would expect the temperature of the hot thing to fall quickly. If it was a good insulator, the temperature of the hot water to fall slowly. Here you're expecting, with a good insulator, the temperature probe 2 to rise slowly. So it's testing your understanding of what an insulating material actually is and your ability to look at a complicated new setup like this and figure out how to apply what you know to it. Temperature probes were connected to a data logger. That's good because they can usually take lots of frequent readings. Figure 2 shows how the temperature measured by probe 2 changed over 10 minutes for each of the materials. So we're not really interested in this temperature probe 1, at least not at the moment. So we've got here, we can see that they all start at 20 degrees C, so that must be room temperature. That's where the insulating material's temperature is before it's connected to the hot metal plate. That would be a control variable. We've connected them all to the hot metal plate, which is 10 minutes. That's another control variable. The independent, the thing we change, is the type of material, and we're measuring the temperature difference really between the start and end of this 10 minutes. So we notice that material C, it's rising quite slowly. We've not got a very big temperature change. That means heat from the metal plate isn't transferring through it very quickly, so it's a good insulator with low thermal conductivity. Material B, the heat is rising a bit faster, so that's temperature is rising a bit faster, so that's a bit of a poorer insulator, a higher thermal conductivity. Now material A, the temperature goes up, but then it plateaus, it levels out, and it stays constant. The reason it would stay constant is if the material is at the same temperature as its surroundings, in this case the temperature of the hot metal plate. Okay, and that's just as the same as you would expect if you have your beaker of boiling water wrapped with an insulator. You would expect its temperature to fall until it reached the temperature of its surroundings, which would be room temperature. So the temperature of the hot plate, read off here, 80 degrees C. because the temperatures stop rising, therefore it must match the temperature of the surroundings, which is the hot plate. Which material is the best insulator? That's going to be C, because the temperature after 10 minutes was lowest. Student repeated the investigation but doubled the thickness for all 3 insulating materials. How would this affect the results of the second student's investigation? So if we've got thicker insulation, that means it's going to be more difficult for heat to get across it. So heat will transfer at a lower rate, we'll have an even lower thermal conductivity, and we would expect smaller temperature rises. So here you're going to get 1 mark for saying we would expect lower temperature rises for all the materials, and the second mark was because there would be a lower rate of energy transfer and a lower rate of temperature increase. Student could have used a thermometer instead of temperature probes and a data logger. Okay, figure 3 shows the data logger screen and a thermometer. So if we zoom in here, okay, I can't really tell whether exactly what number that is to 1 decimal place. I can see it's bigger than 38.5, but it's less than 39. So I might guess it's around 38.7, 38.6, 38.8. But this one, if it's 38.7, I can tell the difference between that and 38.8 and 38.6. And that means this has a higher resolution. Okay, so that's your first advantage of the data logger and temperature probes, is that it's got a higher resolution. The second one, looking at the screen, this is easier to read. So you're less likely to misread it than you are looking at a thermometer. This table gives information about 4 types of insulation that could be used for insulating the cavity walls of houses. We've got 3 different types of wool and a foam, and it tells us the thermal conductivity. So this is testing, do we know what thermal conductivity is? So explain which one of the types of insulation in the table would be best to use for cavity wall insulation. So we want a good insulator here, and we have to know that that means heat doesn't transfer across it quickly, so we're expecting a lower thermal conductivity. So I want to pick this one, polyurethane foam, because, okay, now it's not actually enough for the second mark to say because it's got the lowest thermal conductivity. In this case, they want to know that you know what thermal conductivity means. So the reason is because it's got a lower rate of energy transfer. And you will probably have noticed I've used that phrase rate of energy transfer a lot. That is because it appears on mark schemes a lot. So please try and familiarise yourself with that phrase and remember to use it if questions like this come up in your exam.